Now let's talk about chapter 1.3, HTTP. We're going to talk about HTTP, which stands for Hypertext Transfer Protocol. HTTP is a foundational networking protocol that runs over TCP/IP, the protocol suite responsible for how data packets are transferred over the internet. HTTP is what enables communication between web browsers like one you're using right now and the web servers which host the websites you visit. To understand HTTP, it's useful to know a bit about TCP/IP, even though web developers don't need to dive deep into it. TCP/IP is crucial for moving data across the internet from one machine to another, ensuring the data packets arrive at their destination correctly. While the intricacies of TCP/IP can be complex, what's important for us is to how HTTP uses this protocol to transfer data efficiently. Let's talk about different versions of HTTP. For the most of the web's history, HTTP 1.1 has been the standard. It has served us well, but it has some limitations, especially in terms of speed. More recently, HTTP 2 has been adopted by many websites to address these speed concerns. HTTP 2 maintains the core concepts of HTTP 1.1, but enhances the speed of communication between browsers and servers, making web pages load faster. Looking ahead, HTTP 3 is currently in development and promises even faster communication by using a different underlying protocol called UDP instead of TCP. But for now, we'll focus on the basic HTTP workings and that are common across all these versions. When you access the website, the process starts with the DNS lookup. The web browser extracts the domain name from the URL, such as w3c.org in HTTPS w3c.org, and sends it to a DNS server to get the corresponding IP address. For instance, w3c.org resolves to the IP address 193.51.208.66. The browser then uses this IP address to establish a TCP connection with the web server. Once the connection is established, HTTP functions as a request response protocol. This means that the web browser sends an HTTP request to the web server. Typically, this request asks for a web source like an HTML file, image, CSS style sheet, JavaScript file, or video. In response to this request, the web server sends back an HTTP response. This response usually contains a requested resource or the information completing the cycle of the communication. Whether it's an HTTP request sent from the web browser to a web server or an HTTP response sent back from the server to the browser, both follow a similar structure, consisting of four key parts. First, let's talk about the start line. The start line differs slightly between request and response. In an HTTP request, the start line indicates the HTTP version being used, the type of request such as GET, POST, etc., and the path of the resource. For example, in the request for the Wikipedia page, the World Wide Web, the start line is get/wiki/World Wide Web HTTP 1.1. This indicates that it's a GET request for a specific path using HTTP version 1. For HTTP responses, the start line indicates the HTTP version, a status code, and a status phrase. The common example is HTTP 1.1 200 OK, which indicates that the request was successful. The successful part is the header fields. Header fields provide additional information about the request or response. They are written as key value pairs with a keyword followed by a colon and a value. For instance, in our HTTP request example, we have headers like host, en.wikipedia.org, specifying the host being requested, and the user agent Mozilla /5.0, Chrome /48.0.2564, which tells the server that the type of browser is making the request. In the HTTP response, you might see headers like content length 56,579, which indicates the size of the response body, and the content type text HTML, which tells the browser the type of content being sent. After the headers, there is a blank line. The blank line is crucial as it separates the header fields from the message body. The final part is the optional message body. This part of the message contains the actual data being transferred between the web browser and the web server. In an HTTP request, the message body might be empty, or it could contain data, such as form of inputs from a user. In an HTTP response, the message body typically contains the web source requested, like an HTML page. For instance, in our Wikipedia example, the response message body would contain the HTML content of the World Wide Web articles. To summarize, an HTTP request and response both consist of a start line, header fields, and blank line, and the optional message body. Understanding these components is essential for anyone working with web technologies, as they are backbone of how web browsers and servers communicate. First, let's look at the HTTP request methods. These methods define the type of action a client wants to perform on a resource. The most common request method is GET, which is used when a web browser requests a web page from or a resource from a server. A GET request asks the server to send back the representation of the specified resource. Another important method is POST, which is used when submitting data to a server, such as when filling out and submitting a web form. POST requests create a new resource on the server on the data provided on the message body. Other methods include head, similar to GET, but it only requests the headers and not the body of the resource. Patch, usually applied partially, modifications to a resource. Put replaces the existing resource entirely with the data provided in the request. And delete, as the name suggests, the method deletes a specified resource. Understanding these methods is crucial for web development. Now let's talk about HTTP response status code. These are the 3-digit numbers that indicate the outcome of a request. The most common status code is 200 OK, which indicates the request was successful and the server is returning the requested resource. There are other important status codes as well. 301 moved permanently and 302 found. These codes indicate that the resource has been moved to a different URL. The browser will automatically redirect to the new URL. 304 not modified. The status code tells the browser that the resource has not changed since the last request, allowing the browser to use the cached version. Cached version is basically keeping a copy of the resource on your local caching server, where it doesn't necessarily bring the data from the actual server, but loads it faster from our cached server. 403 forbidden. This indicates the server understood the request, but then client does not have permission to access the resource. 404 not found, one of the most well-known codes. This indicates the requested resource could not be found on the server. 500 internal server error. This code is returned when something unexpected happens on the server and it cannot process the request. These status codes help clients and servers understand the result of their interactions and handle different scenarios appropriately. Knowing these codes can significantly aid in troubleshooting and debugging web applications. URL shortening, a technique used to create shorter, more manageable URLs that redirect to the longer original URLs. This technique is especially useful in situations where space is limited or when you want to make a long and complex URL easier to share. So what exactly is URL shortening? It's a way to take the long URL, turn it into a much shorter version. For example, a long URL like en/wikipedia.org/wiki/URL shortening can be shortened to something like tinyurl.com/URL-wiki. These shorter URLs are particularly helpful on social media platforms like Twitter, where there are character limit for posts. By using a short URL, you have space and make your message more concise. These are several popular services that provide URL shortening, including Bitly, Rebrandly, and TinyURL. These services take your long URL and create a short link that redirects to the original URL. Let's take a look at how the redirection process works. When a user types or clicks on a short URL, the URL shortening service responds with an HTTP response. This response includes a 3.1 status code, which indicates the permanent redirect. It also includes a location header that specifies the original full URL to which the short URL redirects. To illustrate this, let's consider an example. When a user requests tinyurl.com/URL-wiki, the service sends an HTTP request to the tinyurl.com server. The request might look something like this: get URL-wiki HTTP 1.1, with the host header set to tinyurl.com, and the user agent header indicating the browser being used. In response, the server sends back an HTTP response with the 301 moved permanently status code. It indicates the data header showing when the request was processed, and importantly, a location header pointing to the full URL, en.wikipedia.org/wiki/URL shortening. This tells the browser to redirect to the specified Wikipedia page. In summary, URL shortening is a particular way to manage and share URLs more efficiently, and it relies on HTTP status codes and headers to redirect users to original longer URLs. Browser caching is a process where web browsers store web content locally on your computer. This stored content can be quickly accessed in the future, which significantly speeds up loading and previously visited websites. The main benefit of browser caching are faster page loads and reduced network traffic. When you revisit a site, instead of downloading everything again, the browser can load much of the content from the cache. This not only makes the page load faster, but also reduces the amount of data that needs to be transferred over the internet, lightening the loads on the servers. Now, how does this browser caching work? When you visit a web page from the first time, the browser saves some of the content, like images and scripts, to its cache. The next time you visit the same page, the browser can pull this content from the cache, making the page load faster. To ensure that the users see the most up-to-date content, browsers use something called e-tags. An e-tag is a unique identifier for a version of a web source. When a browser requests a cached resource, it sends the e-tag with the request. The server then checks if the resource has changed. If it hasn't, the server responds with the 304 not modified status, telling the browser it's okay to use the cached version. If the content has changed, the server responds with the 200 OK status and sends the updated content along with a new e-tag. In summary, browser caching is all about improving user experience by speeding up access to the websites and reducing the load on the web servers. e-tag play a vital role in making sure that cached contents is always current. Now let's talk about HTTP traffic. HTTP, which stands for Hypertext Transfer Protocol, is used to transfer data between web browser and web server. However, one significant issue with HTTP is that all traffic can be viewed by third parties. This is where network sniffers comes into play. A network sniffer is a type of software that monitors and inspects network traffic. Using a network sniffer, anyone could potentially intercept and view sensitive information such as passwords, credit card numbers, and other personal data being transferred over the internet. This poses a significant security risk, especially for the websites that handle sensitive transactions. To address these security concerns, we have HTTPS, which stands for Hypertext Transfer Protocol Secure. HTTPS encrypts the HTTP traffic data between a web browser and a web server, making it much harder for third parties to intercept or tamper with the data. The encryption is crucial for protecting sensitive information, ensuring that personal and financial data remains secure and during transmission. HTTPS relies on the protocol called Transport Layer Security, or TLS, to secure the data. TLS uses asymmetric public keys to encrypt the communication between the browser and the server. This means that even if someone intercepts the data, they won't be able to read it without the appropriate decryption key. The use of public and private keys ensure that only the intended recipient can decrypt and access the data. For websites to use HTTPS, it must have a digital certificate. This certificate is issued by a trusted certificate authority, or CA, and contains the public key used by TLS for encryption. The certificate verifies the website's identity, ensures users that the site is legitimate, and that their data will be securely transmitted. When you see the padlock icon next to URL in a browser, your browser's address bar, it indicates that the website is using HTTPS and your connection is secure. In summary, while HTTP allows data to be easily intercepted, HTTPS provides a secure way to transmitting information over the internet, protecting against eavesdropping and data breaches. This making HTTPS essential for any website that handles sensitive information.